Alrighty, howdy folks. Let's look at chapter 4 section 9. I agree. If you have noticed that man, he jumped from 4.4 to 4.9. What about the remaining ones? Well, we'll get to them. Okay, so this is a good way of covering the material. So just please trust me, I beg of you. Okay, antiderivatives. What is this? A function uppercase f is called an antiderivative of f on an interval I if f prime of x equals f of x for all x in I. What does that mean? It's a very simple concept. Let me show you with an example. The antiderivative of cosine x is sine x. Okay, why is that? That is simply because what's the derivative of sine x? Cosine x. So the antiderivative of cosine x is sine x. Cool? So when I ask you, hey, what is the antiderivative of something? Let's say secant square x. Immediately you should think in terms of, wait a minute, the derivative of what is secant square x? I remember. Derivative of tangent x is secant square x. Therefore, the antiderivative of secant square x is tangent x. Cool? It's as simple as that. So, in terms of this f of x and all that stuff, would you agree that if I say what is the antiderivative of some cosine x, f of x is cosine x now, then the antiderivative, uppercase f, would be sine x. Why is that? Simply because the derivative of uppercase f, f prime, is nothing but the lowercase f. That's exactly what I was talking about. Okay. Now, many people frown upon the way I am introducing something called an indefinite integral at this stage. They don't want us to do that. They want us to do something called Riemann sum, which I'll cover next, and then talk about a definite integral, fundamental theorem of calculus and all that, and only then introduce the concept of this integral or indefinite integrals, to be more specific. But I think, yeah, all the that's being just pedantic about things. So let's get on with it and say this. The integral of f of x dx is uppercase f of x plus c. That weird looking elongated s, that is read as integral. Integral of f of x dx. You almost never say integral of f of x. You always have to have a dx, dy, du, something like that, the dx. That simply tells you you are integrating with respect to what? Right? In derivatives, this is why I always like to use the concept of dx of something. That clearly tells us we are differentiating with respect to x when we say dx. In the same way, with integrals, if you put a dx, it becomes crystal clear to everybody that you are integrating this stuff f of x with respect to x. Okay, now what does that mean in turn? It simply means the antiderivative, uppercase f, if I want the integral of f of x, I'm simply saying, tell me what is the antiderivative of lowercase f of x? And the answer is uppercase f of x. The only thing is, you have to add a constant, an arbitrary constant, c. Why? Well, the thing is, if you look up, there we said f, uppercase f, is the antiderivative of f of lowercase f. Let me repeat that, I'm sorry. The uppercase f is the antiderivative of lowercase f because the derivative of uppercase f is lowercase f. Right? Okay, if that is the case, what if I were to add a plus c, and now take the derivative of not only the uppercase f, but also of plus c there. Well, the derivative of a constant is 0. So I would still get that f of x back. Whether I add a constant or not, I wouldn't make a difference. So I would actually go ahead and add that arbitrary constant so that it becomes a more general antiderivative. Cool? Okay, so all I want you to know right now is, instead of saying the antiderivative, I will probably use integral more frequently. The difference between antiderivative and an integral is, in the case of an integral, we typically add a plus c. We always add a plus c. Simple? All right. So, armed with that, let's get on with it. We can figure out all kinds of integrals based on our knowledge of derivatives. Let me repeat that. We can find all kinds of integrals of functions just because we know the derivative of different functions. We reverse the process. Okay. For instance, we know that the derivative ddx of e to the x is e to the x. So, the integral of the right side stuff, that is e to the x, must be the stuff on the left hand side of which you took the derivative. So integral of e to the x based on this is e to the x. The only thing is add a plus c. You must add that arbitrary constant. Cool? One integral. Now everybody should know, hey, what's integral of e to the x? Well, simple, man. E to the x plus c, because the derivative of e to the x is e to the x. Integral of e to the x must be e to the x. Okay, and this is something we already looked at. Knowing that the derivative of sine x is cosine x, immediately we can make up an integral problem out of this. Integral of the right hand side, cosine x, must be the left hand side stuff, sine x. Integral of cosine x dx equals sine x. The only thing is add a plus c. Cool. The derivative of cosine x is negative sine x. So integral of what now? Well, according to this, we need to say integral of negative sine x equals cosine x. Would you agree? Based on the pattern that we saw, we should say integral of negative sine x is cosine x. It turns out you can multiply both sides by a negative, and instead you can say integral of positive sine x is negative cosine x plus c. Cool. So, would you agree? Now put thought in a slightly different way. Would you agree that if I took the derivative of negative cosine x, I would get negative of negative sine x, which is positive sine x? That's what we have here. So integral of sine x is negative cosine x. However, the derivative of sine x is positive cosine x. So please be sure to remember that. Similarly, earlier, integral of cosine x is sine x, even though the derivative of cosine x is negative sine x. All right. And here is a very important one. We know that the derivative of x to the n, the power rule, says the derivative of x to the n is nx to the n minus 1. So what is the derivative of x to the n plus 1? Simple, right? Instead of an n, we have an n plus 1. So we say n plus 1 times x to the n plus 1 minus 1. That n plus 1 minus 1 is simply n. So the derivative of x to the n plus 1 is n plus 1 times x to the n. Why am I saying this? Oh, that's because now I can say integral of n plus 1 times x to the n is x to the n plus 1. Isn't that neat? I can say the integral of this right hand side is the n plus 1 x to the n is x to the n plus 1 plus c. However, we can divide both sides by the constant. N plus 1 would be a constant, and so in fact we will actually say integral of x to the n dx is x to the n plus 1 over n plus 1 plus c, where n can be any real number as long as n is not equal to -1. Why is that? Why can't n equal -1? Oh, it cannot, because what happens to the denominator when n equals -1? Oh, that would go to 0, right? So n equals -1 cannot be included in this context. And also, there's one more reason. When n equals -1, does this become x to the -1? Integral of x to the -1? What is integral of x to the -1? Well, integral of 1 over x. What is the integral of 1 over x dx? How do you answer that? You answer it by saying, hey, wait a minute. Do I know the derivative of something equals 1 over x? Can you recall? The derivative of what equals 1 over x? The derivative of natural log of x is equal to 1 over x. Would you agree? So if the derivative of natural log of x is 1 over x, the integral of 1 over x actually must be natural log of x plus c. In fact, we will say natural log of absolute value of x plus c. So for that special case where n equals -1, we do not have this form of result at all. That's the idea. Cool. Next, the derivative of tangent x equals secant square x. Make up an integral problem from this yourselves, please. Integral of secant square x dx is tangent x plus c. Cool. Cotangent x is negative cosecant square x, the derivative. So integral of cosecant square x should be negative cotangent x plus c. Cool. And derivative of secant x is secant x tangent x. So integral of secant x tangent x is secant x plus c. And cosecant and all of these work exactly the same way. Okay, all of this you already know. And here comes the one that I was just discussing. The derivative of natural log of absolute value of x is 1 over x. So integral of 1 over x dx is actually natural log of absolute value of x plus c. Cool? All right. And also, we know about some inverse trig functions, the derivatives. The derivative of sine inverse of x is 1 over square root of 1 minus x squared. Right? I asked you to memorize all of these things. So from this, you can actually say integral of 1 over square root of 1 minus x squared is sine inverse of x plus c. Okay? Let's see. Some of you who are probably more astute, could you recognize something here? Yeah, what I wrote is definitely correct. Let me ask you, what is the derivative of cosine inverse of x? That's just -1 over square root of 1 minus x squared, right? Would you agree? Cosine inverse x, the derivative is -1 over square root of 1 minus x squared. So, could we say, based on that, the integral of 1 over square root of 1 minus x squared dx is negative cosine inverse of x? Could we say that? The answer is, of course, yes. Usually people do not use that form. They use this form. But if you were to say, well, I want to say this is negative cosine inverse of x plus c, nobody can object to it. Cool. What happened here, man? Okay, the derivative of tan inverse of x is 1 over 1 plus x squared. That implies, I think the text box size was weird. Yeah, let's Where are we? That's all I needed to do. Okay. Where are we? Go back to this. The derivative of tan inverse of x is 1 over 1 plus x squared. So integral of 1 over 1 plus x squared dx is tan inverse of x. 12. Secant inverse x is 1 over x square root of x squared minus 1, and so on. Now here comes a very interesting one. The integral of a constant multiple of f, meaning if you have to take the integral of some lowercase f of x dx, but you have in fact a c constant multiplying that, then you can pull that constant outside of the integral. Kind of like the derivative stuff, right? d dx of c times f of x. You pull that c out and say c times d dx of f of x. In the same way, for integrals, you can yank the constant multiple out. Just as the derivative of a sum equal to sum of the derivatives, integral of a sum is equal to sum of the integrals. What does that mean? If you need to take the integral of some f of x plus g of x, then go ahead and take the integral of f of x and the integral of g of x separately and add them. That's perfectly all right. Okay. Similarly with subtraction. However, what is very, very, very important is the integral of a product is big tam not equal to, I should have made this equal sign much bigger. Big tam not equal to the product of the integrals. Just as the derivative of a product is not equal to product of the derivatives, the integral of a product is not equal to product of the integrals. Similarly for division, right? If the integral of a quotient is not equal to the quotient of the integrals. Cool? This is what I would like for you to know. To me, this is not very different from something that you already learned. So just a bit of a twist to what you learned. All right, please make that change. And then let's use this concept to solve all kinds of problems. In your book, at this juncture, they never say find the integral of something. Okay, instead they say find the most general antiderivative of the function. By that what they mean is find the antiderivative and add a plus c to it. Duh, that's the same thing as the indefinite integral, right? So we can restate that question in terms of a definite integral, and that's what I will do. Your book may say find the most general antiderivative of blah blah. I'll say, oh, you mean integral? Yeah. So your book actually has this as find the most general antiderivative of x minus 3 the quantity square. I changed it to what's the integral of x minus 3 the quantity square. Okay. Integral of x minus 3 the quantity square? Whoa. Did we have any formula for something like this? The truth is no. So how do we do this? Well, let's FOIL this out. Integral of x squared minus 6x plus 9, that's what x minus 3 the quantity square becomes, right? Okay. Now, is the integral of a sum and difference equal to sum and difference of the integrals? So that means, can I split this as the integral of each component? X squared. What's the integral of x squared? Do you remember? Earlier I said integral of x to the n dx is x to the n plus 1 over n plus 1. Does x squared look like x to the n? What is n? N is 2, right? So the integral should be x to the n plus 1, that is x to the 2 plus 1, which is x cubed, over 2 plus 1, which is 3. So the integral of x square is x cube over 3. Are you cool with that? Minus 6 times, can I yank the 6 outside? Yeah, it's a constant multiple, so I can yank that 6 out. What's the integral of x? Integral of x? Well, that looks like x to the 1. So n is 1. So the integral of x to the 1 is x to the 1 plus 1 over 1 plus 1. That is x square over 2. Right? And what's the integral of 9? 9 can be pulled outside. Integral of 1 dx. The derivative of what is equal to 1? The derivative of x is equal to 1. So the integral of 1 is x. Are you following me? Let me repeat that. If I ask you for what is the integral of 1, you should say, wait a minute, what's the derivative of what is equal to 1? We know the derivative of x is equal to 1. So the integral of 1 is just x. So the integral of 9 would be 9 times x, because 9 came out as a constant multiple. So we end up getting x cube over 3, like I said, minus 6 times x square over 2, that's x square over 2 is the integral of x, and 9x plus c. We can simplify this and say 6 over 2 is 3 and write it this way. I'm thinking this is not all that complicated. Okay, I'll work quite a few problems. Verification. Ooh, they not only want you to find the most general, but check your answer by differentiation. No big deal. What they're saying is we should be able to take the derivative of this thing and be able to get the stuff inside the integral, the integrand it is called, probably the foiled form. Let's do that. What's the d dx of x cube over 3 minus 3x squared plus 9x plus c? Derivative of x cube, 3x squared, 3x squared over 3, or rather 1/3 times 3x squared, minus 3 times the derivative of x squared is 2x. The derivative of 9x is 9. The derivative of constant is 0. There we go. If you simplify this, you get x squared minus 6x plus 9. Ta-da! That's the foiled form of the integrand. Right? So our answer must be right. Because when we claimed, or when we found that integral of this is equal to this right-hand side, we verified by checking that the derivative of this is equal to the integrand. End of the story. Cool. That looks a little complicated, but we are ready for it. What's the integral of 3? What's the integral of 1? We just talked about it. What's the derivative of what is equal to 1? X. So integral of 1 is x. Integral of 3 therefore is 3 times x. Cool. What's the integral of sine x? The derivative of what is equal to sine x? Or the derivative of negative cosine x? Right? The derivative of cosine x itself is negative sine x. So if you want the derivative what is equal to positive sine x, you have to say the derivative of negative cosine x is sine x. Right? So we know exactly how to integrate the first two terms. 4 over square root of x? Yikes. Well, should we be worried about that 4 multiplying? Nah, that can be pulled outside. That's a constant multiple. So apparently we need to know what the integral of 1 over square root of x is. Okay, 1 over square root of x, what is the integral of that? Well, think of it as x to the negative 1/2. Is that true? 1 over square root of x is nothing but x to the negative 1/2. Oh, okay. Is that in the form of integral of x to the n dx? Yeah, n happens to be -1/2. So the integral of x to the n is x to the n plus 1 over n plus 1. So the integral of x to the -1/2 should be x to the -1/2 plus 1 over -1/2 plus 1. That's all there is to it. And when you do that, so let's see. So for the integral of 3 is 3x minus 4 times the integral of sine x is negative cosine x. And this turns out to be x to the -1/2 plus 1/2, plus 1 rather, is x to the positive 1/2, which is x to the is nothing but square root of x. Okay, over negative 1/2 plus 1/2 becomes in the denominator over 1/2, which is what became 2 times. Please check this yourself. So that's what we have. Cool. I didn't even take the derivative of this. Let's see if I can take the derivative of it quickly. What's the derivative of 3x? 3. Yep, that's the first term. What's the derivative of cosine x? Negative sine x. 4 times negative sine x is -4 sine x. Yep, checks out. What's the derivative of square root of x? This is one of those things I wanted you to memorize. 1 over 2 square root of x. Would that simplify to 4 over square root of x? Yep, there we go. So our answer is right. Cool. Now, find f given f triple prime of x is equal to this. Any idea? It's a bit unfair on my part. Hey, how do you do this? I never taught you anything like this yet. But let's see. Let's go back to derivatives for a second. If I give you f and ask you to find f triple prime of x, can you get to f triple prime in just one shot? No, you cannot. You have to go in sequence. Given f, you find f prime. Looking at that f prime, you take the derivative of that f prime, you get f double prime. Take the derivative of f double prime, you get f triple prime. So you go in sequence. So if now we are given f triple prime of x and asked to find f, we have to go in a sequence. From f triple prime, let's figure out what f double prime is. And once we get f double prime, let's figure out what f prime is. And from there, we'll go to f. By applying what process? How do you go from f triple prime to f double prime? Well, integrate. Cool. So to find f double prime, we will integrate f triple prime. And that's exactly what I'm saying here. F double prime of x is integral of f triple prime of x dx. And so f triple prime happens to be this. Cool. Are you ready to tell me what this integral ought to be, folks? Integral of 3, 3x. Integral of e to the x. The derivative of e to the x is e to the x. So integral of e to the x must be e to the x. The integral of sine x, negative cosine x, right? So plus, I said plus c1. I thought you should say plus c, man. C, c1, c2, c3, c0. They are all equally arbitrary constants. In fact, you will see why I chose to call this c1. Pause the video if you need to. And can you anticipate why I might have called this as c1? If you figured it out, you should pat yourself on the back. Okay? If not, don't worry about it. Cool. So I took the constant, arbitrary constant, or integration constant to be c sub 1 at this stage. Cool. Now that we got f double prime, Would you agree the reasonable thing to do is to find f prime of x by integrating f double prime? That's exactly what I'm doing here. So 3x minus e to the x minus cosine x plus c1. Let's integrate that. You tell me. 3x. What's the integral of x? X square over 2. X to the 1 plus 1 over 1 plus 1. So x square over 2. Integral of e to the x is e to the x. Integral of cosine x, the derivative of what is cosine x? Oh, positive sine x. So the integral of cosine x itself is just sine x, but we have a negative sign here. So the integral of negative or minus sine x. Are we supposed to integrate this c1 also? You bet. Right? You must integrate that c1. But I don't know how to integrate a constant, man. Liar. Didn't you know how to integrate a constant 9 here in the first problem? Wasn't that simply 9 is a constant multiple? You could pull that out. An integral of 1 dx. Integral of 1 is x. So isn't that simply 9 times x? Had this been a constant 7, what would you have said? 7x. 5, 5x. Pi, pi x. C1, you got it. Man, you're a genius. Right? C1x, as simple as that. Should we have another integration constant here? Yep. Every time you integrate, you generate a new constant. So, that's why I call the original one as plus c1, so that in the second stage of integration, I would have another constant, and I want to call that as c sub 2. Cool? Are you getting the hang of this, folks? All right. Now that we got f prime, let's get f by integrating f prime. 3x squared over 2 minus e to the x minus c1x minus sin x plus c1x plus c2. Yikes. X square integral x cube over 3. E to the x integral e to the x. Sin x negative cosine x. C1x c1 x square over 2. C2 c2x. There's another constant coming. C3. Cool. So, guess what? Given a f triple prime of x, we were able to find f of x by simply integrating. If any of you are going to take physics in next semester, you will bump into this kind of stuff quite a bit. You will be given what's called acceleration, and you are expected to find the position. And to do that, you integrate acceleration, you get velocity or speed. And then you integrate the speed, you get position. Okay, so this kind of stuff is useful in many, many places. Next, find f given f double prime of x equals this. And whoa, f of 0 equals 2. F prime of 0 equals 3. I wonder why they gave that. Let me go back to the previous one. If they had given something like that, in this case, let's say f double prime of 0 equals 5. Could we have done anything about that? Would that piece of information have helped us in any way? Okay, let me okay, we got f of x to be no, I cannot go here. So I do have to go to the first one. If we were given f double prime of x of 0 is 1, what can we do with that? Guess what? f double prime of 0 means x, when x is 0, f double prime will be equal to 1. Let me repeat that. Given f double prime of 0 equals 1 means when x is 0, f double prime will be 1. So we will say 1 equals f double prime of x, in this case would be 1, is equal to 3 times 0 minus e to the 0 minus cosine of 0 plus c1. So they all would have some value, and you can figure out that constant c sub 1, the exact value of that integration constant. That's the reason these conditions are given. F of 0 equals 2 and f prime of 0 equals 3. I'll show you exactly how they are useful. Okay? Alright, so again, given f double prime of x, there is no way to find f directly. We need to go to f prime of x first and then integrate that to get f. So f prime of x is the integral of f double prime of x, cube root of x minus x, integral of that, minus cosine x rather. So I wrote cube root of x as x to the 1/3 so that we can exploit that power rule of integration, x to the n. The integral of x to the n is x to the n plus 1 over n plus 1. So x to the 1/3 plus 1 over 1/3 plus 1. But 1/3 plus 1 is 4/3. So the integral becomes x to the 4/3 over 4/3. Are you with me? The integral of x to the 1/3 would be x to the 1/3 plus 1 over 1/3 plus 1. But 1/3 plus 1 is 4/3. So we have x to the 4/3 over 4/3. Let me ask you. Instead of saying over 4/3, could I flip that and say times 3/4? That's typically what I do. X to the 4/3 over 4/3, but in the next step I'm going to write this as just 3/4 times x to the 4/3. And the integral of cosine x is positive sine x, so we have a subtraction going on, so minus positive sine x. And the integration constant c sub 1. And this is nothing but 3/4 x to the 4/3 minus sine x plus c1. Now we can use that condition f prime of 0 equals 3, which means when plug x equals 0 and f prime of x equals 3 into the equation that we just got. So 3 equals 3/4, 0 for x, so 0 to the 4/3, minus sine 0 plus c1. 0 to the 4/3 is just 0. And sine 0? Oh, dang. You mean I need to know the trig function values? Yes, you do. Sine 0 is 0. So the first term goes to 0, the second term goes to 0, and on the right side we just end up with a c1. So guess what? c1 is 3. So we were able to figure out the exact value of that constant based on this condition f prime of 0 equals 3. Cool? So f prime of x, in this case, is whatever we had with a c1 replaced by what we just found it to be, that is 3. Cool? Now we need to find f. So let's integrate f prime of x. And so x to the 4/3, the integral is x to the 4/3 plus 1 over 4/3 plus 1. 4/3 plus 1 is 7/3. X to the 7/3 over 7/3, or maybe I may have said 3/7. Yep, see, I don't even go over 7/3. Instead I say times 3/7, you mean. 3/7 x to the 7/3. And integral of sine x is negative cosine x, so I have a minus negative sine x plus 3x, and absolutely make sure that you add an extra constant c2. And when we simplify this, 3 times 3 is 9, 4 times 7 is 28. X to the 7/3 minus negative cosine x is plus cosine x plus 3x plus c2. Let's plug the conditions. Now apply the condition, that is plug x equal to 0 and f of x to be 2. We are in business. Cosine of 0, however, is 1. 3 times 0 is 0. This guy goes, first term goes to 0, second term is 1. And so we get 2 equals 1 plus c2. So that means subtract 1 from both sides and you get c2 to be 1. So that means f of x, go back to this one and replace c2 with a 1. Cool. So let's see. Excuse me. Another problem just like that. In this case, we are given f of 0 and f of 1. Whoa, Nelly. I like these. F of 0 and f of 1. So as before, let's find f prime of x first by integrating f double prime of x. Simple polynomial. So it turns out to be that. 6x, 4. The integral of 4 is 4x. 6x square over 2. That becomes 3x square. 24x cube over 3 becomes 8x cube, right? Cool. And plus c1. So let's integrate f prime of x to get f of x. 4x square over 2. So 2x square. 3x cube over 3. Just x cube. 8x to the 4 over 4. 2x to the 4 plus c1x plus c2. Cool. Okay. So now we have two arbitrary constants, c1 and c2. But we are given conditions f of 0 and f of 1. So let's apply those conditions. F of 0 equals 3. That means plug x equal to 0 and f of x equals 3. And we get c2 to be directly 3. Okay. Now apply the condition f of 1 equals 10. That is plug x equals 1 and f of x equals 10. But notice we already know the c2, so I made sure that I plugged in that c2's value here. And for x I plugged in 1 and for f of x plugged in 10. That's on the left hand side. And when you simplify this, you end up getting c1 to be 2. 2 plus 1 is 3, 3 plus 2 is 5, 5 plus 3 is 8. So 10 minus 8 is 2, so c1 equals 2. Cool. You might have a problem like this. And so f of x now is completely known. There are no arbitrary constants in it. All right. Folks, that concludes this section. I tell you, a lot of people make such a big deal about this as if this is some kind of an esoteric thing. It's not. At least this part of integration is fairly straightforward. And I would rather you think of these as integrals, but understand this is the same thing as antiderivative. What's the difference between an indefinite integral like this? Oh, by the way, why am I calling it indefinite integral? Because there is something called a definite integral, which we will learn in a couple of sections later. But right now, when this integral is just an indefinite integral, and indefinite integral is exactly the antiderivative plus a constant, arbitrary constant. Cool? All right. That's it, folks. Thank you.